The great thing about coming to CppCon is you get to see many, many interesting people and many interesting problems that are solved.
Okay, so welcome everybody. Thanks for coming to my talk. I will be talking about two different things today. I will be talking about the tools we have in C++ to do error handling in the first part of my talk. And the second part of my talk, I will be talking more about what errors to handle and how to do that in practice. So I've been programming C++ for a while now, and I've been at ThinkCell the whole time. And we have a very small team, but we have over 1 million very active users, and they use our software on normal desktop computers. And that's a very hostile environment because we don't control it. People can control anything, install anything they want on there. Administrators have very specific ideas on how to configure those machines. There's security tools that can interfere with you. So long story short, in order to ship a stable product that could become successful, we had to have excellent error handling and error reporting just to get our product into a stable state. But first, before I begin, let me clarify what I mean by error handling. That's a super wide field. And when I think about error handling, I think about errors, I think about, well, what can go wrong? And when I think about systems where you have to deal with something going wrong, I first think of these things, right? This is working in hardcore mode. Here, lives are at stake, quite a lot of them actually in the case of this plane. And I researched a little bit, just out of curiosity, how do those systems work? It turns out, just so that you learned something today, like those modern airplanes, they have typically 3 primary computers, each of which can control the entire plane. And then they have a couple of other backup systems. In separate locations, they have different hardware. They often implement the same software spec by different teams just to make sure you're not hit by the same software bug either. And these things must survive ramp faults due to cosmic radiation or engine explosions or things like that. What we do, this is something that we typically call engineering for reliability, right? This is a reliable system that can survive in this case, probably destruction of parts of its physical system. Error handling is something far simpler. We deal with programmer error, mostly. We deal with unforeseen system configurations, unforeseen system behaviors, but we will assume that your RAM works. We will assume that your computer doesn't explode suddenly. And if you're lucky, like I am, to work in a field that is not especially security relevant, you can always fall back to doing this. So this is error handling in easy mode, of course. So, but why do we bother with this? Well, like I said, we ship software that runs sometimes in unexpected environments. The users do unexpected things with them, and we make mistakes. And I think I'm quoting Andre already, bad error handling breeds bugs. But we can sink enormous effort into this error handling code. But at the end of the day, we're not paid for writing perfect error handling code. We are paid for delivering customer value. We are paid for solving our users' problems, right? So the goal is not writing error handling code per se. The goal is just to get to a stable product as fast as possible. And good error handling is key to achieve that. So in my talk, I will first go over the error handling mechanisms that we have, starting with the most basic. And then in the last part of my talk, I will talk about how we handle errors at ThinkCell in practice. What do we handle? How do we do that? So let's start with the basics. C-style error handling. Everybody knows this function, the POSIX function, to open a file at a certain path. Now, this thing mixes its return value, the file handle, with an error code, right? Because this thing returns either a valid file handle or -1 on failure. And if you open the man page, you will see that this can set the global error no variable to some error. And there's a long list of error cases that this thing can set. From the benign that you probably should handle, end, the file doesn't exist. Okay, I can expect that. To the slightly weird, interrupt, this call was interrupted by a signal. Okay, I guess I have to retry this. To the weird, fault, the path was outside the address space. I don't think I have to handle this. This is, if at all, a program error, probably. Maybe it's an uninitialized variable, but it's nothing I should handle, per se. And there's a long list of more error cases. The situation on Windows is very similar, of course. Create file also mixes its return value with its error code. It returns either a valid file handle or invalid handle value. And it also sets a global error variable that you can query by calling getLastError. So same interface, similar problem. And there are functions like that in the C++ standard here. String to long converts the string to a long, of course. On success, it returns the parsed integer, unsurprisingly. If no conversion occurred, it returns 0, as if that weren't a valid long. It also sets the end pointer, probably to the beginning of the string. And it also sets the error variable. And then on overflow, similar situation, it clamps the value, but again, it returns a valid long and sets error. There are just a lot of things that you have to check to get this correct, right? And to check if an error occurred. So this is a very inconvenient interface. But unfortunately, this is never going to die, and we need good tools, at least until Herb Sutter gets this way, and everybody programs with C++ and reflection. But as long as operating systems have C-style interfaces, this is not going to die. And we need good tools to even handle these kinds of errors. First, in C++, we invented exceptions to make this a little bit more elegant. And exceptions get a bad reputation sometimes. People call them glorified go-to statement. People say they're difficult to reason, or it's difficult to reason about the control flow that's introduced by exceptions, that they are horribly slow when they're thrown and caught. And some people, like the Google folks, ban them in their code base. And they require, of course, and that is certainly true, require you to write exception-safe code. When I wrote this, I went back to the Google C++ style guide to check what they said about exceptions. And I quote, they say, "Our advice against using exceptions is not predicated on philosophical or moral grounds, but practical ones. Things would probably be different if we had to do it all over again from scratch." Which I interpret as meaning that their main problem is actually making old code exception safe. I might be wrong, but that's what I read into this.
You're right.
Thank you. I can read. But exceptions can be exactly the right tool in some situations. Here I have a very simple piece of code. You see I wrote this for CPP on C, so I query the weather in Folkestone. We do an HTTP request to some JSON API. We parse the return JSON. We write something to a log file. So every line here could realistically throw, right? Somebody pulls your network cable, something returns different kind of JSON format suddenly, or your disk is full. And maybe, for example, in the case of the JSON parser, this error is detected deep in the stack of this JSON parser. So the unwinding of the exceptions, the unwinding of the stack here is actually a feature. It's very, very practical. I talked to Khalil yesterday, who does this awesome work about making exceptions faster, and he told me he had people who wrote a JSON library come to him and say, hey, we want to switch error handling to exceptions because in this stack, we have to check return values so often, it actually impacts our performance. But of course, there were some criticisms, like exceptions can make your code hard to read and hard to reason about that are entirely correct if you don't catch exceptions as locally as possible, like I did here. Well, there are very nice aspects of exceptions as opposed to return codes. They have more semantic error information. These exceptions are structs, they have names, we can attach more data to them if we need that. And of course, our code on the happy path remained entirely clear of error handling. So these are all very good aspects, I think, in programming. And that, last but not least, if you heard it in his keynote, Bjarne likes them. So what am I going to say? Some points remain kind of true. They are a little bit slow on the error path. Exceptions are serial. That means there's only ever one that can be in flight at the same time. This can be a problem. And of course, code must be exception safe. That's just the truth. There's a very good talk 2 years ago by Pete about the misuse of exceptions. It's a very good collection of cases where he found exceptions misused while he was doing code reviews and how he cleaned that up. A very good talk that I can recommend. So what would happen if we could combine the advantages of return codes, their simplicity, with the advantages of exceptions, their semantic richness? And luckily, somebody had this idea. Thank you for being here. And now I can ask you, is that the first, did you have like prior work you built this idea on? That is it, right? Okay. So Andrei Alexandrescu had exactly this point to make in this talk 2012. What if we could combine the advantages of those two? It's a very good talk. And this is how std expected was born. Quote, last quote, I think. Let's make exceptions the error code. So this is, and then the advantage would be, well, more simplicity. We could have multiple error codes in flight at the same time. We could store them, they're just variables. We could store them for later. We could move them across threads. We could collect and transform them, etc. So how do we use std expected? Here's everybody's favorite error handling example, parsing an integer. I have a very simple function, parses an integer from a string view, and it returns an expected, which is either the integer or the error condition we encountered. But here I'm not so much interested in how to parse integers. I'm more interested in what to do with this result. So let's say I want to build on parsing an integer, and I want to parse an integer and then invert this parsed integer and divide 1 by this integer. So parseInt returns me an expected. Expected has a very simple interface. I can convert it to bool to check if there's a valid value inside this expected. If it is, I can access this value and do something with it. And here now I check if this integer was 0, because then I can't divide by 0. Std unexpected is a convenience constructor that I can just give it my new error message, and this will be automatically converted to the std expected of a double and string I want to return here. And if I don't have a 0 in my integer, I can return the 1 divided by the integer as I want. In the else part, I can access the error as well with .error and convert that. Now that's a very simple interface, but that's not how we, I guess, should program. That's not how we should program with std expected. That's not the most convenient interface, I think. Std expected also has a very elegant monadic and functional interface. And there are a couple of functions. I want to point out 3 here. There is std expected transform. That's a function that will only be called if the std expected contains a valid value, and then you can transform that value. Transform error is similar. It lets you transform the error that is contained. And then is also a function that is only called if the std expected contains a valid value, and it lets you transform the entire std expected into another type of expected. So here we transform the integer, we transform the error from a simple enumeration to a string that is more user readable, and finally we do the same as before. We check if our integer was 0, and otherwise we divide 1 by that integer. So this is a very elegant interface. I think how we should program with std expected. This function now does not contain any explicit flow control statements. That makes it much easier to reason about the program state. It makes it much easier to understand that we've really covered all cases and didn't miss a case in this long line of if then else statements. And that makes it harder to make mistakes. So I think that std expected is going to be maybe the default way how we return errors in C++ in the future, because it is very powerful and at the same time very, very simple. You can, by the way, if you have questions, you can ask anytime. We have questions at the end too, but if you want to interrupt me. Yes?
Is the transform and transform error, could those be inverted? Like, is there a requirement sort of like you must handle things first, then do the, is there a...
I think I could have changed the transform and transform error. And so the transform error transforms the error type, in this case from an enumeration to the string. I think I had to do the and then at the end, right? Because by then I already have a state expected of a string, and now I return more strings. I think that's, I had to do it this way. So that lets me come to the next C++ feature I want to present shortly today, because I also think it's related to catching and handling errors, even if it's a different kind of error, and that's contracts. So contracts, the contracts paper that I've linked to here by Timur, who's also here and program chair at this conference, is a very long paper. It's a very readable paper. It's a very thorough proposal. And despite its length, it's conceptually very, very simple. He has written this blog post himself, Contracts Explained in 5 minutes. And that contains the basics, or the most important things you have to know. So in short, contracts are a more flexible, new standard assert mechanism. And as opposed to the previous mechanisms, it's not for checking environment behavior, different behavior of my operating system functions. It's to express invariance in our code. It's to guard against program error, of course. We can write better asserts. We can write pre or post conditions on our functions. And one of the best features in this contract proposal is that we can configure at build time what actually happens if one of those contracts is violated. So here's a very simple example, little function. We have a precondition that checks this argument is not 0. If you write a precondition, the precondition can only access the function arguments, of course. The variable that you capture in that precondition x here is implicitly const, so you don't by accident mutate one of your function arguments. We can write post conditions. These post conditions can also capture the return value, here captured as R. And they can also refer to function arguments to establish a relationship between the two. If a post condition refers to a function argument, then this function argument must be declared const. It's not only implicitly const, you must declare it as const to make sure you didn't by accident mutate this function argument inside the function body. This post condition wouldn't make any sense then. And we can just write better asserts, contract asserts. And they're better because they're not just a macro that is automatically removed in release builds. It's configurable. So when are these things evaluated? This is all very, very sensible defaults. Unusual for C++, I know. Preconditions are initialized after, or are evaluated after the arguments have been initialized, of course, because you can access them, but before the function body runs. Post conditions must be evaluated after the return value has been initialized, otherwise you couldn't capture it, but before the destruction of local variables, which might again manipulate state inside your function. Contracts support exceptions in the sense that if you throw an exception inside a contract assert, this leads to a contract violation. Again, very sensible. And they're also supported in const expr context, and then they turn into compiler errors, of course. And I said initially that contracts, the behavior of contracts can be configured at build time. And there are 4 different semantics we can choose from that define what happens if a contract has been violated. So first is the ignore semantics. That means, well, we do nothing if the contract is violated. We can configure observe semantics, which means a contract violation handler will be called that can do anything you want, but then the program execution continues. And force semantics mean the contract violation handler will be called to do logging or whatever, and then the program will terminate. Or we can do quick enforce, which means we terminate as quickly as possible. And at CppCon, John Lakers had kind of a good, he presented a good intuition which use cases should use which contract semantics. So in our case, desktop application, not especially security relevant, we have always implemented observe semantics. So we do error handling, error reporting, and then we hope for the best and just continue. Because the worst that can happen is that the program crashes, but that's better than annoying the users with error messages. Enforce would be Bloomberg itself, maybe. You know, and something goes wrong, you have enough time to do logging, you want to find out about this problem, but then you terminate because you don't want to lose millions of dollars. Quick enforce is a medical device. Something is out of spec, you stop immediately, you don't have time for logging. And we can also customize the contract violation handler. Here, very simple sample code, I think directly from the paper. You just have to define the global function, handle contract violation, that here receives an instance of this contract violation, and you can check what the semantics were, and then most importantly, defer to your own error reporting mechanism, maybe, or the default implementation. Contract assertions may have side effects explicitly. Logging, for example, sending error reports would be a side effect. But the paper says they're not allowed to have destructive side effects. And a destructive side effect would be a side effect that affects the correctness of your program. In a correct program, contract assertions should be redundant. If you take them all out, like with ignore semantics, your program must still work. Otherwise, you've made a very serious mistake. The assertions themselves, of course, should also be complete and independent. They shouldn't have side effects that change the correctness of a future pre or post conditions, right? Anything is possible in C++, but that's not what you should do. And they have zero overhead in the sense that if you choose ignore semantics for your contracts, then it should have no impact on the program behavior. So contracts are also a huge feature that I'm very much looking forward to, and I see one very important advantage especially. If currently you're using any libraries, like Boost, for example, then very often you will have code like this somewhere in the very beginning of your code base that configures what Boost assert does. And then that configures that Boost assert should somehow relate to your own assert mechanism. And I hope that if libraries use contracts, that we could hopefully all get by with a single contract violation handler for all the libraries that we use. That would be very nice. So the last C++ feature, also C++ 26, I want to mention is library hardening. Library hardening means that we now want to enforce the pre and post conditions that we have always documented in the standard. The standard says, you know, the precondition of dereferencing an iterator is that this iterator must probably be pointing to a valid element or something like that. But we never enforced any of these things. We never asserted them. It would just crash, hopefully. Maybe in release builds, maybe it would not crash. So now we want to enforce them. We want to insert contract asserts for all these pre and post conditions. Microsoft had something similar for a long time. They had debug iterators that we've used all this time that helped catch a lot of bugs. And these will also be based on contracts in the future. So Clang supports this, GCC supports this, Microsoft supports this. As far as I know, well, I guess I can't. So none of those use contracts yet. Neither does Clang, neither does Visual Studio. They all just assert and possibly terminate the program, but at least the asserts are there and they help you write correct programs. Any questions so far? Everybody who asks a good question gets one of those Think Cell socks. I have four pairs of socks left. So we have so many options in C++, so many good options, but we have so little time. So what do we do in practice? As I've said, we're not paid for handling errors. We're paid for solving customer problems. So we have to focus. We have to focus on the areas where it matters most. And we want to have very good tools for handling errors, otherwise our programmers won't do it. So we must have error handling tools that are easy to use in our own, not only the standard tools, but tools in our own custom libraries. All error handling code that we have must be tested, otherwise it probably doesn't work anyway. And we must focus all the efforts where it matters most. In practice, probably very few areas in your code will have like most of the work in error handling. So what do we do now in practice? When we program, we use any other external API, often operating system, but not necessarily. We check every single API call. So here I have two examples, very simple APIs, getting the host name on POSIX systems and Windows. The getHostName function will return 0 on success. We write this, and it will also set the error variable if it failed for some reason. So we have this error macro around that will check if the error variable has been set to anything. On Windows, there's a similar contract. Typically, Windows API functions return 0 on success, I think. And if they don't return 0, then they will also set this getLastError thing. So we have API-R, this macro, that checks for those things. So we check every API call, and we make this very, very easy. In fact, we have different wrappers for all kinds of return code pattern that we find on Windows, on macOS, and whatever, that check this error variable, getLastError. We have one for H results. And we want to make sure, even in code reviews, right? That's the first thing you look for in a code review. Did the programmer think about all these error codes that might be returned? We are so trained to do this that we even have an annotation returns void to make sure that we can annotate that we thought about the error handling, but this thing doesn't return any error. So there's nothing to do. Because otherwise in a code review, I would immediately say, what about this guy? You forgot the error handling. We also use asserts aggressively to assert preconditions, postconditions, invariants, and these stay in release builds. We use noExcept by default, unless we, of course, know that something is going to throw an exception. In that case, as with returns void, we also annotate function as throwing, although that doesn't have any standard meaning. It's just an annotation.
In returns void, do you actually check if it's void?
Oh, we might. I didn't look for that. I hope we do. I hope we do. We should. No, yeah. The way I know us, we probably do, but I didn't check. So we use noExcept by default. We also annotate functions where we know this throws. So I didn't forget the noExcept. This actually throws, even though there's no language feature to annotate this. Writing too much noExcept, of course, might cause our program to terminate. But if I didn't know this was throwing, and I'm not handling the exception anyway, then this would have terminated at some point anyway. So we might terminate right away. What we do instead is install a terminate handler to be notified when we wrote a noExcept where we shouldn't have written one, or where we just forgot the exception handling, right? So now we've annotated everything. We check for all these return codes. What do we do with them? Well, by default, we assume that everything works. All these functions will never return an error. We just will catch any error that they ever return. And the goal here is to keep the set of code paths small. We don't want to write error handling code where we don't need it, where we can't reproduce it, where it's not going to be tested, and that's where it's going to be wrong. We want to keep our program simple and the set of program states small. The only exception, of course, are the cases where you know beforehand that this is an error that will happen, right? Opening files is the classical example. And here, opening a file, there are a lot of cases. And again, we try to handle them in a way that's as simple as possible. So here, opening the file would return a non-negative value on success. That's the file handle. It might return an invalid file handle and interrupt. In this case, we have to retry. And then there is a list of error codes where we know they can happen and that we can live with. Opening the file will just fail. The file didn't exist. We don't have access rights to this. There is no space on the disk, whatever. The typical file error scenarios. We could probably reproduce them. And if we can reproduce them, then we will, of course, handle them. Same on Windows, same with the API error. Here's the list of error codes that I know can happen. I want to ignore them. If any other error is returned from removed directory, for example, error out of paper, I want to be notified. So what do we do now when one of those checks fails? The first priority is we want to collect as much information as possible. So our client application sends an error report. It automatically creates an error report that contains the entire stack as a mini dump on Windows and also as a mini dump on macOS, and these only contain stack memory, so they're only maybe a few hundred kilobytes of size, and we send them home to our backend. Our server application, that's just a private server for our own backend, would hold the thread and notify the administrator so that the administrator could look at a live system and see what's going wrong. And the second priority, like I said, is to carry on. The behavior is now undefined, but that just means we will disable any further reports. We do not terminate, especially not after asserts. You don't even show error messages for asserts. Asserts are just code. They can be wrong. We want to make sure our programmers write a lot of asserts, they write a lot of invariants, and we want to incentivize them to do so. And if the customer calls anytime you get the assert wrong, then people wouldn't write as many asserts, I guess. So this is the observed semantics in the contracts world. And now we get a lot of error reports. If there's 1 million customers, everybody encounters a wrong assert a couple of times. And we collect them in our backend, and we have this little application that we can use to look at them and to filter them and to find out what are the most frequent scenarios. And very often, of course, we find scenarios that we could never reproduce in-house. People where the software, or clients where the software interferes with some crazy security software, where administrators misconfigured the system. Timing issues because they use them on very slow machines. All kinds of different issues. So we can look at the operating system where this bug occurred, which versions of our software. We can do a full text search. For each individual bug, we see the line in the code where this occurs, in which versions, in which time spans, etc. And the cool thing here is that this database actually establishes a two-way communication between the client that encounters the problem and us, because here we can enter the build in which this bug has been fixed. And when another customer encounters the same bug, it will send the bug report to us. The backend will notice, hey, this is fixed in this version. It will reply with that version. The client will automatically download and even automatically install this update. And the customer will just never have this problem again. It will just, in the best case, it will just be silently be fixed. And here's more information, which customer states, etc. So this allows us, it also allows us to ask customers to pop up messages and say, yeah, you are encountering this bug. Could you tell us more about this? Please contact support. So we gather more information and we try to reproduce this error at home, because we want to add handling only for errors that we can reproduce, right? So that the error handling is testable. And in the best case, we find an actual fix for the problem, an actual workaround, instead of just showing the message box I've shown you initially. And we do one other thing to customize the behavior, and I think the contract proposal is also working on extending contracts to enable that, because we categorize the errors we encounter by their severity. And this affects what we do when we encounter one of those errors. So there are critical errors, null pointer access, for example. If any of these API calls failed, or if an assertion failed. That means that these are errors that are always severe and that shouldn't happen because they are always programmer errors. So we don't have to write handlers for them. We just want to be notified when that happened. The program, like I said, is afterwards in an invalid state. No further error reports will be sent. So we send the error reports, we disable reports. We typically don't show messages to the user at all. And the next less severe error category is what I would call a situation that is somewhat untested. It's defined behavior, but unclear how this could happen. So here's a little code example. We get a range, maybe a range of bytes, and I want to extract the Unicode code point value out of that. And I assume here, I want to verify, that this is always a valid code point. Because I couldn't reproduce that this is not true. But here also the error handling is very simple. I can always return the Unicode replacement character. So this is like a defined behavior situation. I know what happens if my assumption is not true. I just want to be notified if this is ever not true. So theoretically this could happen. We do send an error report. We don't disable further error reports. We just throttle them because this might happen often, unfortunately, if we have bad luck, but we still continue execution as normal. One step below that still is maybe something that is a third-party bug. We encounter a bug in something else we are interoperating with. We can handle this, we have reproduced this, we support this, we have tested this, but it degrades the user experience a little bit. So users may complain to us, and they may call our support team. So this is maybe something that we would always log, but we would never report to our backend. We know about it already. But if a user ever complains to our support team, we can just look in the log file, we see this is the problem, and we can politely show them where they should direct their anger, so to speak. And then one priority still below that would be a weird system configuration, maybe. So on Windows, for example, you can configure your decimal separators, and you can say that the space character should be your decimal separator. This has some surprising effects. Not every software can deal with that. We have, again, reproduced this. We support this. We can live with this. But again, it could still cause weird problems. So that's something we log only in debug builds, maybe. But again, people will call us and say, I have this weird problem, and we can figure out, yeah, that's probably the space separator thing. So we can our support engineers can set a flag on the system that would then enable logging this even in release builds. Because that might be the reason for the support call. Okay, and then we have all these error scenarios. We recently had a talk with Timur, was curious about how people use errors in practice. So I hope some of that makes it into the next contract proposal. And as I've said, we do error reporting. We send a stack to our backend. So we have our own system that is somewhat similar to Google Crashpad, but we can report all kinds of errors. So whenever our program encounters a failing assert, unexpected API return code, we launch an error handling process, and we do out-of-process error handling. And that's something you should always do, because if your process encounters an error, you don't know what state your process is in. Maybe it is not able to send error reports anymore. So we do this out of process. We suspend the process that had the error, collect all the information we need, create the mini dump, and upload this if customers gave us permission to do so. And then we do analysis on the server side. We symbolicate, we load these mini dumps, we symbolicate them, we group them by the location in the code base where they occurred, so that we can then get to this visualization and find the locations in our code that cause the most problems and fix them first. And with that, I am almost on time at the end. Thank you very much for your attention. And we still have time for questions in exchange for socks. Yes?
Hi. I'd love to hear your thoughts on stood error code versus stood error condition and error category and custom error categories.
Here you go. Yes, we don't use those. And we don't use those because we found they were at the wrong level of abstraction. So when we started doing cross-platform programming, we had to remove all kinds of Windows dependencies out of our code base and introduce cross-platform interfaces. And we actually never had a scenario where we wanted to transport the cause of a problem out. We captured this in a different way. Let's say you have a file operation, creating a temporary file, writing to a temporary file, whatever. Very deep in this file abstraction, somewhere you do the actual call to fwrite, where you have to do this error handling. And there's just a list of things that are allowed to happen. Space, disk full, whatever. And in those cases, I throw this exception out. There are all the other cases, error out of paper, that are not allowed to happen. I want to report them. But outside, the user that is trying to write to a file, he doesn't care why this failed. I just know JSON parsing, HTTP request, files, they can fail for a list of permitted reasons. But typically, I don't care why. I don't care if it's the request that failed or the response, or This is something we never actually did. So and the cases where we do care about the error codes is very close around the operating system function. And this is where I don't want any cross-platform abstractions, because how does error sharing violation on Windows translate to any mangled up error condition? It's like I don't even want to think about it. So create file can return error sharing violation. I have to deal with this, and then I can deal with this or not. So this is something we never found a use for, to be honest. Yeah.
So regarding STD expected, I was wondering if you had any thoughts about what kind of error you would return from like a virtual function. So let's say, for example, we have a class called runner, and then we have with a virtual function called run that returns STD expected with some error we're trying to decide. And there's two implementations. One is like a dog. So you can ask a dog to run, which can run successfully, or it won't run because it's tired or it's hungry. Or
right.
Whatever. And then we have another implementation of runner, which is a car.
Yeah.
You can
and then it has
some.
some.
Yeah, out of fuel.
Yeah.
Battery is dead. And like, dogs don't have batteries or fuel, and cars don't have moods. So like, I guess like, what would you think about?
In this made-up example, yeah. Here. So my favorite answer is always to other programmers when I review, and it's the same answer like before, right? Figure out if you really need this. Even for STD expected, it's the same argument, right? STD expected has very, very good competition, and that is STD optional. It's for something can fail, but I don't care why, right? There are arguments, maybe you care why because you want to show a better error message, and so I get this. And then you need to transport something out. But if that's the case, you probably also know exactly what the error scenarios are and what you have to report. Right? So it's hard to say in a made-up example. I don't know. Yes.
So before, when you were talking about things still doesn't operate in a very high security environment, and so when you encounter an error, right, or an assert fails, carry on as much as you can. Do you see that as a potential trade-off for security risk, right? Once your program enters an undefined state, something is happening that's wrong.
Sure.
Right. That something could be a security.
Sure. If our software weren't just a simple Office application, then yes, you would be right. But so far, the worst thing that can happen is that the editor crashes. So that's the comparatively benign. Yeah. Thanks. But true. Yeah. If we were in other environments, we would do something else. Yeah.
I just won the last sock. No.
You got it.
Seriously, what do you think about expected not throwing exceptions from the destructor? Is something that you would have missed, or
still expected not throwing exceptions from the destructor?
Yeah. Yesterday I talked with Andrei Alexander School that proposed this likely class that is the origin, very, very primitive origin expected. And then the special thing about likely was that it threw from the destructor if you didn't check the error code, which is brilliant. But people don't like destructors, exceptions from destructors for many other reasons. But that would have made expected really, really special, and not just another type of optional.
Throwing, you could still assert, but even then, I'm not sure. Like with all the other cases I had where I don't even care that much about the error code, I'm not sure it's a good design choice. I can have an API that out of, because they have a library, if I would write a library, I would probably have to use still expected and return the error code. Mm-hmm. But like I said, in our application, maybe we don't even care about it. Mm-hmm. It's just allowed not to work, and that's fine. Yeah. So I wouldn't check it. And if you want that, you could still use an assert, right? That would also work.
Okay, thank you.
Yeah.
Thanks for the talk. I guess you have a no socks error, but we can
ignore I don't have. No.
Since you mentioned code reviews, I was just wondering how you can ensure that the developer has thought about all the errors, exceptions, or the error codes that the function can return and handle it. Is it a manual process? Do you have to look at the docs and then figure out, or is it?
Yes, and then you have to know who you are reviewing. If you occasionally probe if this is really all there is. Yeah, it is. Yeah, it is something you also have to learn, I guess, at some point how to read this, how to thoroughly read this, how to distinguish the cases that can happen. I find the Microsoft documentation very, very good, for example. They often explain what can happen. Yeah, it's something that is a manual process. Oh, yeah.
Thanks for the talk. Is it like
I think you have
a
to
good
turn this
idea?
down a little bit. Even
Is it a good idea to try and save like as much as user data as possible before allowing your program to crash?
Is it a good idea what to?
To like try and save as much user data as possible?
Yes, but trying to save as much user data as possible, of course, is a good idea. But most applications today do this, right? You crash and you open it again and you end up where you were. So this is luckily a largely solved problem. Yeah. Anybody else? Otherwise, thank you for your time and enjoy the conference.